Force. So, what's a force? Well, our operational definition, an operational definition just suggests that that's a definition that we can actually use rather than it just being sort of more abstract. Our operational definition of a force is that a force is an interaction between two objects. It is an interaction between two objects. The force is that actual interaction. Now that interaction will be experienced by both of the objects that are interacting, of course. So if I clap my hands together, then there's a force there when my hands are in contact with each other. This hand is pushing on this one, this direction. This hand is pushing on this one, in this direction. Right? But there's only one interaction. There are not two different forces. There's one interaction. It's experienced by this hand, and it's experienced by this hand. There's only one interaction, and that interaction is that force. Okay, so what are some typical kinds of forces that we are interested in? There's a force of push or pull, or force of some contact. Maybe that's the kind of force that we think about. That's sort of what our mind defaults to, that when we think of a force, we think of something pushing or pulling on something else. And I think in general, thinking of a force as a push or a pull is not a bad way to think about it. But it kind of misses some things, perhaps, like field forces. In particular, the one that we're going to be interested in is the force of gravity. I'm using a lowercase g there because just like this, I might say force P of like push or pull, or sometimes we say force A for applied force. Those are some typical ways of abbreviating those. And this one we're going to abbreviate F and then a lowercase g for force of gravity. So the force of gravity is a field force. Something just needs to be near a large object that's making a pretty significant dent in the fabric of space-time, like the planet Earth, for example. There's a big dent around the planet Earth in space-time, so things tend to want to go toward the middle of that. Something doesn't need to be touching the Earth to experience the force of gravity because of its proximity to the Earth. For example, the Moon is orbiting around the Earth because of its gravitational interaction with the Earth. Those would be that interaction between those two objects. It's a mutual interaction. And of course, things can be touching the Earth or be getting as close to the Earth as they can before they're stopped by like a lab desk and this little platform and this piece of paper. That's being supported now by those things, but it's still experiencing that force of gravity downward. The force of gravity on something is also called its weight, so sometimes we just use a W for that. And many things, like that pen I was just talking about, are experiencing a supporting force, which we could call force of support. Like right now, maybe you're sitting at some kind of desk or something watching this video, and that desk, the chair that you're in, or if you're lying on a bed or whatever, wherever you are, there's a supporting force on you that's stopping the force of gravity from just pulling you down toward the center of the earth. It is pulling you down toward the center of the earth, but you're not moving toward the center of the earth because there's a supporting force on you. And we will usually call that the normal force. A normal force, if you look up normal in the dictionary, there's a couple definitions there that you would expect, not weird or conforming to expectations or whatever, things like that. But around the fifth definition or so, you're going to find that normal has a technical definition in the sciences that normal means perpendicular. Perpendicular. So why do we call this a normal force? Because that supporting force is always perpendicular to the surface that is providing the support. Okay, so there's some typical forces there, and we're going to talk a lot more about the interactional nature of forces and other things like that. But right now, I just want to give you a quick crash course in how to make a force diagram. Force diagrams, also known as free body diagrams. What's so free about them? Well, the body is whatever object we're talking about. And the freedom is that we have liberated the body from its context and we're only talking about that object. So, for example, we have a table and we have a book that's sitting on that table. If we're going to make a free body diagram, then I represent the book with a dot, liberating the book from its confines and context here. That's the book right there, that dot. And so what forces, if we wanted to make a free body diagram, that should include all of the forces that are acting on the book. What forces are acting on the book? Well, every single free body diagram that you make for everything, unless I ask you to make a free body diagram for something that's out in deep space, should have this force of gravity, and will also have a supporting force. And there it is, not moving, so those forces are balanced. Great. Now, how about this? How about if we take the same book, but now there's going to be an applied force pushing this way, and the book moves with a constant velocity across the table. So, kind of like this. Let's see what that would look like. Well, the force of gravity and the normal force are still there, and they're still exactly the same as what they were. There's no motion in this direction, so that means those forces must be balanced. Now, the book is moving in this direction. That's that applied force. But there's also friction present. So how much friction is there? Here's a question for you. I'd like you to pause the video for a second. Is there a smaller amount of friction than this? Is there an equal amount of friction to this? Or is there more friction? This. Which one is correct? And there is a correct answer. It does not depend on anything. The answer is what it is. Go ahead and pause. All right, welcome back. I wonder what you chose. Well, if this force of friction was smaller than this applied force, that would mean that there was extra force in this direction, which would be like extra tapping on the bowling ball, like from broom ball. That would be like extra in that direction, and that means that the book, would be getting faster in this direction. Likewise, if the friction force was more than this, then the motion would be changing this way. There'd be like extra. There's tapping in that way. So if the velocity is constant, just like the bowling ball through the no-touch zone, if the velocity is constant, that means the forces must be balanced. Which brings us to force misconception number 1. If an object is moving to the right, there must be a force acting on it in that direction. Of course, you could substitute any direction you want for right, just using that as an example. There must be a force acting on it in that direction. Direction. There we go. Nope. Not true. You should be able to convince yourself pretty easily that that is not true after having watched Broomball. The ball, for example, as it rolls through the no-touch zone, is rolling forward. It keeps moving in the direction that it's moving, and it does not require a force. There's no broom interacting with it at that time. If you're thinking, well, the broom did interact with it and the ball remembers. No, of course the ball doesn't remember. The ball has no idea how it acquired the motion that it has. It just is moving, and unless there's some kind of unbalanced force or tapping, you could think of it, if you're making the analogy to broom ball, if there's no tapping or extra force in any direction, then its motion is going to stay the same. So what is true is that if the forces on an object are balanced, its motion will not change. And likewise, if the forces are unbalanced, then the motion will change. What do we mean by the motion? When we say its motion will change, really what we're talking about, the way that we quantify the motion of something, that's its velocity, right? Its velocity will not change. So if something's velocity is constant, that means the forces must be balanced. If the forces on something are balanced, that means its velocity must be constant, which could include the possibility that it's constantly zero, right? That it's not moving. All right, I think that's pretty much all you need to know. I'm just going to give you a couple more quick examples of force diagrams and leave you to it there. An object in free fall, no air resistance. Well, if there's no air resistance, then there's no supporting force. What is there on this object? There is only the force of gravity. And, well, that's not balanced, right? So the motion of this object will be changing. It's not just going down at a constant velocity. It would be, well, it could be going up. There's another misconception that looking at this force diagram, is this the force diagram for an object that has an upward velocity, a downward velocity, a zero velocity, or could it even have like some other velocity? The answer is it could be any of those things. This is just the force diagram or free body diagram for an object that's in free fall with no air resistance. It could be anywhere in its path. So for example, if we're talking about like a ball that was launched upward like this, like your projectile ball lab, it could be here. When the object is right here, what forces are acting on it? Gravity. Only. What about when it's right at its peak? Oh yeah, well when it's at its peak, well there's no gravity. Just kidding. Of course it's gravity. It's the same exact thing, and when it's here, it's the same exact thing. And until it hits the ground, this is the only force that's acting on it, if we assume that there's no air resistance. Right? So we don't know where it is. Could be going up, down, whatever. But we do know that there's an unbalanced force in the downward direction, so its velocity will be changing according to this imbalance. All right? Let's see what else. How about a car braking that's going in this direction? Well, car would have the force of gravity on it. It would have a supporting force from the road, call that a normal force. And then if it's going this way, is there a force in this direction, forward? No, unless you're like holding the brake pedal down and the gas pedal at the same time. But that's really not a good idea. There is a braking force, which is really like a friction force, right? That way. How could the car be moving in this direction but have this unbalanced force in this direction? Well, the fact that there's unbalanced force in this direction means that the velocity is changing in that direction, which means that it's slowing down. So, of course, that's possible. And that's the whole point of braking. Want to slow down. Let's see, what else? So sometimes we have objects on ramps. This is going to be something that we want to get good at. So here's a book, and it's sitting on this ramp, but there's enough friction so that it doesn't slide down. So what would that look like? Well, when you put something on a ramp, I'm going to make a little dotted line here to represent that ramp, try to match that angle as best as I can. So when something's on a ramp, then gravity tilts over to the side. Just kidding, gravity doesn't care at all about us and our physics books and our projectile balls and all this. Gravity just pulls on things toward the center of the Earth. It's always straight down. Now, the support force here on this is, we call it a normal force because it's perpendicular to the surface always. So here, I'm going to actually tilt the paper here so I don't have to strain my artistic abilities too much and draw this support force. How big is it the same as this? No, it's not the same as this, at least not entirely. So if you think about what's going on with this gravitational force, if we break a force, which is a vector, it's got a magnitude and a direction. For example, the force of gravity always toward the center of the Earth, what we will usually call down. If we break that vector into components along an xy axis system, or you can think of it as ij directions, that are parallel to and perpendicular to the ramp, then we can see, to get from here to here, if you imagine this as like the hypotenuse of our little vector component triangle, I could get down and over. Notice that this is parallel to, I'm not going down here and over. This is the hypotenuse. This is a right angle. Then the support force must be balancing this part of the gravitational force. And if this is not moving, well, there must be some friction, and that friction would be up the ramp. And how much would there be? There would be exactly the right amount to balance that. And there, if we did a little sine cosine, if we actually knew the angle and had some numbers here, we could break this into the two components and actually figure out what the magnitudes of those are. And I think that's the example that I will leave you with there. So right now we're not interested in doing any of the math. We're just interested in this idea of forces either being balanced or unbalanced. Forces are balanced when something is not moving or when it's moving at a constant velocity. Constant velocity or zero velocity, that is when forces are balanced. If the motion is changing, then in other words, if you have acceleration, then that's when there's some unbalanced or extra force in some direction. All right, try making some force diagrams.